In the year 2150, a spacecraft leaves the solar system carrying something no human-made machine has ever carried before, a destination beyond our Sunday. Its target is only about 4 light-years away. By cosmic standards, that is almost next door. By human standards, it is an abyss. The spacecraft is not heading toward another planet in our solar system. It is leaving the solar system entirely, crossing the darkness between stars, toward a world whose existence was first confirmed more than a century earlier. Proxima Centauri b, a rocky planet orbiting the nearest star to our Sunday. We know it exists. We know roughly how massive it is. We know it circles its star every 11 days or so. We know it lies in a region where temperatures could, under the right conditions, allow liquid water, but there is one thing we still do not know: what is actually waiting there? And in 2150, humanity is finally going to find out. The first problem is distance. Light travels faster than anything else we know. It crosses the distance from Earth to the Moon in just over a second. It reaches Mars in minutes. It takes hours to cross the outer solar system. But Proxima Centauri is different. Its light takes about 4 years to reach Earth. That means every photograph transmitted from the spacecraft will already be more than 4 years old by the time people see it. And if the spacecraft needs an answer from Earth, that answer will take another 4 years to return. There will be no live conversation, no remote control, no waiting for instructions. The mission must think for itself. That alone changes the meaning of space exploration. For centuries, every human journey has remained connected to Earth. Even astronauts on the Moon were only a few seconds of communication away. Mars missions operate across a delay, but engineers can still send commands and receive data within minutes. A mission to another star breaks that relationship completely. The spacecraft becomes an independent explorer, and that independence is only possible because of another problem humanity spent generations learning how to solve: speed. A conventional chemical rocket would take tens of thousands of years to reach Proxima Centauri. Even the fastest spacecraft humans have ever launched would still require many thousands of years. So the mission of 2150 cannot simply be a bigger rocket. It needs a fundamentally different way of moving. The concept that inspired the first serious studies of interstellar probes was surprisingly simple. Do not carry all the fuel. Let the fuel stay behind. Instead of pushing a spacecraft with an engine throughout the journey, enormous lasers on or near Earth could fire a concentrated beam at an extremely thin reflective sail. The photons themselves provide the push. Each individual photon carries only a tiny amount of momentum, but billions upon billions of photons striking a large, lightweight sail can produce a tremendous acceleration. The spacecraft becomes less like a traditional rocket and more like a microscopic sailboat sailing on a river of light. Decades before humanity could realistically attempt an interstellar mission, engineers were already studying concepts based on this principle. The goal was extraordinary: accelerate a tiny spacecraft to a significant fraction of the speed of light. At 20% of light speed, the journey to the Alpha Centauri system could take roughly 20 years. That is still a lifetime for some people. But it is no longer thousands of generations. It is a mission that could be designed, launched, and completed within the span of a human life. By 2150, the technology has changed dramatically. The spacecraft leaving Earth is no longer a fragile laboratory experiment. Its scientific instruments are miniature. Its computer systems are designed to survive radiation and decades of autonomous operation. Its navigation system can recognize stars and calculate its own position without waiting for Earth. But the hardest problem remains: how do you stop? Accelerating to another star is only half the journey. If the spacecraft reaches Proxima Centauri at 20% of light speed and has no way to slow down, it will cross the system in minutes. That might be enough to take photographs. It would not be enough to explore. A flyby could reveal the planet's color, clouds, atmosphere, and perhaps even signs of surface features. But a mission that can enter orbit could study Proxima b for years. So the engineers of 2150 face a brutal requirement. The spacecraft must somehow throw away an enormous amount of kinetic energy after traveling 4 light years. One possibility is to use the star itself. a giant magnetic or photon sail, could interact with the light and charged particles around Proxima Centauri, gradually reducing the spacecraft's speed. Other designs could use lasers positioned in the destination system. Some might rely on magnetic fields, electromagnetic braking, or combinations of several techniques. None of these ideas are easy. At interstellar speeds, even a tiny particle becomes dangerous. A grain of dust that would be harmless to a spacecraft moving through the solar system could release enormous energy in a collision at a significant fraction of light speed. So the spacecraft needs protection. Its forward shield is designed to absorb or deflect microscopic impacts. Some systems use layers of material separated by gaps, allowing an incoming particle to break apart before reaching the main structure. The spacecraft also needs to survive something even more difficult: time. 20 years of flight is not merely 20 years of travel. It is 20 years of radiation exposure, 20 years of mechanical stress, 20 years in which electronics can fail, software can become corrupted, sensors can degrade, and tiny problems can become mission-ending disasters. And all of this happens while Earth continues moving around the Sun. Proxima Centauri continues moving through the galaxy, and the spacecraft crosses an almost empty ocean between them. Then, sometime in the 21st year, the star begins to grow brighter. Proxima Centauri is no longer just a point of light. It is becoming a destination, and this is where the mission becomes scientifically interesting. Because when Proxima b was discovered in 2016, scientists did not discover another Earth. They discovered a possibility. The planet is roughly Earth-sized and at least somewhat comparable to Earth in mass, depending on the measurements and models used. It orbits a red dwarf star called Proxima Centauri, a star far smaller and cooler than our Sunday. Because the star is so dim, Proxima b can orbit incredibly close to it and still receive an amount of energy that places it within what astronomers call the habitable zone. That phrase has caused endless confusion. The habitable zone does not mean a planet is habitable. It only means the planet receives the right approximate amount of stellar energy for liquid water to potentially exist on its surface, assuming other conditions are suitable. Earth sits in the Sun's habitable zone. Venus sits near its inner edge. Mars lies near its outer edge. Yet none of those positions alone tells us whether a planet actually contains life. Proxima b could have an atmosphere. It could have oceans. It could be frozen. It could be dry. Its atmosphere may have been stripped away by radiation. Or it could have a climate completely unlike anything found in our solar system. One reason is its star. Red dwarf stars are common in the Milky Way, but they can be extremely active, especially when young. Proxima Centauri produces powerful stellar flares and high-energy radiation. For a planet orbiting so close to its star, this could be a serious problem. Over long periods, stellar radiation and charged particles can erode an atmosphere, but the outcome depends on many factors. The planet's gravity matters. Its magnetic field might matter. Its atmosphere might replenish itself through geological processes. Clouds could alter its climate. Oceans could move heat around the planet. Even its interior could influence its long-term habitability. And there is another strange possibility. Proxima b may be tidally locked. That means the planet could rotate once for every orbit around its star, keeping roughly the same hemisphere facing the star. If so, one side would experience permanent daylight while the other remained in darkness. Between them would be a region of perpetual twilight. But even this picture is more complicated than it sounds. A thick atmosphere could transport heat from the illuminated side to the dark side. Ocean currents could redistribute energy. Cloud patterns could change the amount of sunlight reaching the surface. The climate might be nothing like the simple frozen dark side and burning day side picture imagined in early discussions. And this is why the spacecraft matters. From Earth, scientists can infer astonishing amounts about planets they cannot visit. They can measure a star's tiny motion. They can watch a planet pass in front of its star when the geometry is right. They can analyze starlight filtered through an atmosphere. They can search for molecules that might reveal chemistry associated with biological activity. But Proxima b does not conveniently pass in front of its star from Earth's perspective. That makes atmospheric observations much more difficult. For more than a century, telescopes have been forced to study the planet indirectly. Now the spacecraft is finally close enough to look at it directly. At first, there is almost nothing to see. The planet is only a point against the glare of its star. Then the onboard telescope processes the light. A disk begins to emerge. Not a photograph like the ones taken of Earth, not a landscape, just a tiny world resolved into a handful of pixels. But those pixels contain information. The spacecraft measures how the planet reflects different wavelengths of light. It watches how the brightness changes as the planet rotates. If it rotates in a way that produces observable changes, it studies the infrared glow from the atmosphere and surface. It searches for clouds. It searches for evidence of water. And most importantly, it searches for an atmosphere, because the atmosphere is the first great dividing line between a world that might support life and a world that almost certainly cannot support life as we know it. The instruments detect gases, carbon dioxide, water vapor, if present, perhaps methane, perhaps oxygen, and this is where the mission reaches its most dangerous scientific moment. Because finding a molecule associated with life is not the same as finding life. On Earth, oxygen is strongly associated with biology because photosynthetic organisms have filled our atmosphere with it. But oxygen can also be produced through non-biological chemistry under certain planetary conditions. Methane can be biological. It can also be geological. A single gas cannot solve the mystery. Scientists need context. They need combinations of molecules that are difficult to maintain together without continuous replenishment. They need to understand the planet's chemistry, its star, its atmosphere, and its geological history. And even then, the strongest conclusion might not be that life has been found. It might be that the evidence is unusually difficult to explain without biology. That distinction matters, because after more than a century of searching, humanity still has no confirmed evidence of life beyond Earth. Not microbes, not fossils, not civilizations, not artificial signals. The universe has given us possibilities, but not proof. Proxima b therefore represents something more profound than a destination. It is a test. If the closest potentially habitable world is sterile, that tells us something. If it has an atmosphere but no detectable life, that tells us something else. If it has chemistry suggesting biological activity, the implications become enormous. And if the spacecraft finds unmistakable evidence of life, the question changes forever. We would no longer be asking whether life exists elsewhere. We would be asking how often it happens. The answer could transform our understanding of biology, because life appearing independently on another world would suggest that biology may not be a one-time accident confined to Earth. It would mean that the universe has produced life at least twice, and suddenly the night sky would look different. Every star with a planet would become a potential laboratory. Every ocean world, every rocky planet, every atmosphere would become part of the same larger question. How common is life? But the spacecraft has another mission. It is searching not only for life, but for technology. A civilization advanced enough to transform the environment of its planet might leave detectable traces. Artificial radio emissions, powerful laser signals, industrial chemicals in an atmosphere, night-side illumination, other signatures that nature would be unlikely to produce on its own. These are called techno-signatures. Yet the absence of a signal would not prove that Proxima b is uninhabited. A civilization could be silent. It could communicate in ways we do not recognize. It could have existed millions of years ago. It could live underground or beneath an ocean. It could simply be too technologically young to produce detectable emissions. The search would therefore remain an investigation, not a verdict. And perhaps that is the most important lesson of the mission. The spacecraft does not travel 4 light-years to confirm a story humanity has already written. It travels there to discover which story is true. Maybe Proxima b is a barren rock stripped by its star. Maybe it is a frozen world with a thin atmosphere. Maybe it has oceans beneath clouds. Maybe beneath those clouds, chemistry has crossed the boundary into biology. Or perhaps the most surprising result is something nobody predicted. A planet unlike Earth, but still capable of supporting life in a completely different environment. that possibility forces us to confront one of the deepest assumptions in astrobiology. When we search for life, are we searching for life itself? Or are we searching for life that resembles us? For centuries, Earth was the only example we had. Every biological rule came from one planet. Every cell we studied descended from the same ancient lineage. Every ecosystem we knew used chemistry that evolved here. A second living world would give us the first opportunity to compare two independent experiments conducted by nature. That comparison could be more important than the discovery of any single organism. It could tell us whether life tends to emerge when conditions are right, or whether Earth represents an extraordinarily rare accident. And there is another layer to the story. The spacecraft itself is a message, not necessarily an intentional message to anyone who might be waiting. A message in the simplest possible sense. We crossed the distance. For most of human history, the stars were destinations only for imagination. We could measure them, name them, build stories around them, but we could not travel to them. In 2150, that boundary has finally been crossed. The spacecraft approaches Proxima b after decades of flight. The data begins its journey home. 4 years pass. On Earth, generations have grown up knowing the mission was coming. Some of the people who designed its earliest systems are long gone. Others are elderly. Some were not even born when the spacecraft launched. And then the first complete scientific dataset arrives. Not a dramatic revelation from a single image. Something more valuable. Measurements, atmospheric spectra, surface maps, weather patterns, geological clues. A record of an alien world assembled one observation at a time. Perhaps there is life. Perhaps there is not. The mission may answer one question and create 100 more. That is how science usually works. The closer we get to reality, the more complicated reality becomes. And perhaps that is what makes this journey worth taking. The greatest discovery may not be a second Earth. It may be the realization that Earth was only the beginning of our search. 4 light years once sounded like an impossible distance. In the year 2150, it becomes a road. A very long road. A road that takes decades, demands technologies that have not yet been invented, and carries machines into a darkness where no human has ever stood. But the destination is no longer imaginary. Somewhere around a small red star, there is a world. For more than a century, we have known only its mass, its orbit, and the faint influence it exerts on its star. Soon, perhaps, we will know its atmosphere, its climate, its geology, maybe even whether something is alive beneath its sky. And when that first message finally crosses the 4-year gulf back to Earth, humanity will face a strange realization. The most distant place we have ever reached may also be the place that brings the universe closest to us. Because for the first time, we will not be looking at another world through a telescope. We will have gone there. And whatever we find on the other side of the darkness, one fact will already be certain. The age when humanity could only wonder what lies beyond the stars will be over.